Imagine waking up on a freezing winter morning in Finland. Outside, the ground is covered in snow. But inside the local school and library, the rooms are warm. To the people inside, this comfort feels completely ordinary. In the town of Pornainen, that warmth begins somewhere that looks entirely out of place. It starts inside this 13-meter-high black cylinder. This structure holds 2,000 tons of crushed rock. When fully charged, the internal temperature of this mass averages 400 degrees Celsius, about 750 degrees Fahrenheit. This capacity corresponds to roughly a week of the town's winter heat demand. It is called a sand battery, though its scale and thermal storage method distinguish it from any conventional battery. Traditionally, solving winter cold is a direct process. A boiler burns fuel at the exact moment a building needs heat, but electricity operates on a more complex schedule. Grid availability, wind generation, and market prices can change dramatically from one hour to the next. This diagram shows the core mismatch. The moments when electricity is cheapest and most abundant rarely align with the morning hours when thousands of people need to heat their buildings. The sand battery bridges this gap. It consumes grid electricity when it is most useful to the system, converts it into heat, and saves that energy for later. The entire facility functions as a buffer, allowing the town to exploit the difference between when energy is generated and when it is actually required. The process begins with grid electricity powering large resistive heating elements. Much like a standard electric heater, these elements turn electrical energy into heat, but here they are used to warm a continuous stream of air. Industrial blowers then drive this hot air through a closed-loop network of heat transfer pipes buried deep inside the storage material. The storage material is 2,000 tons of crushed soapstone. This local industrial byproduct, a side stream for manufacturing heat-retaining fireplaces, provides a cheap and effective thermal mass. This material keeps the heat from leaking away because thermal energy moves through crushed stone relatively slowly. In a 1-meter thick mass of sand, it would take over 8 days for a 500-degree temperature on one side to reach 100 degrees on the other. Scaling the battery up actually increases its efficiency. As an object grows, its volume, where the heat is stored, increases faster than its surface area, where heat escapes. The hot interior remains protected by the massive outer layers of cooler stone. This industrial scale is a physical requirement. This massive volume is what allows the system to hold its energy for days at a time. When the heating network needs energy, the airflow reverses. Cooler air circulates through the pipes, absorbing the stored heat from the surrounding stone. This newly heated air reaches a heat exchanger, where it transfers its thermal energy into water. This hot water connects the battery to the town's existing district heating network. These insulated underground pipes are the hidden utility system that moves thermal energy from a central plant to individual buildings. The water travels through this network to warm the local school, library, and offices. Because the battery plugs into this existing infrastructure, the entire mechanical chain remains invisible to the people experiencing the warmth. Think of capacity as a water tank and power as its output pipe. The battery doesn't dump all its heat at once. It releases energy at a controlled rate, acting as a buffer to meet the town's demand as it rises and falls. However, this system has a specific limitation. It cannot return this energy to the grid as electricity. It is designed strictly to deliver heat. This one-way conversion is a deliberate choice. By storing energy as heat, the facility provides the exact resource the customers actually want, while bypassing the complexity of chemical storage. This storage creates economic flexibility. By using software to shift electricity consumption to off-peak hours, the project owners reported purchasing power at prices roughly 70 to 80% below the market average. The system's reliability was proven during the 2025-26 winter in southern Finland, the sixth harshest winter of the 2000s for the region. During that test, the operators reported 0 interruptions in heat delivery and over 85% efficiency, while successfully eliminating oil consumption in the network. This performance is the result of a massive physical chain: blowers, air channels, thousands of tons of mass, insulation, heat exchangers, and underground pipes. These 2,000 tons of stone provide a week of energy flexibility for the town. By decoupling power generation from the immediate demand for heat, the system allows the municipality to move its consumption across the week. This facility stores time.